So, hello friends. Today we are going to see thermomechanical or mechanocaloric effect. I am Dr. Gerald Anthony, Assistant Professor in Chemistry, St. Xavier's College, Palangote. Here you can see, so you can consider two vessels, but both the vessels are having same type of compound, and but may both the same compound is maintained in two different vessels. Now if a temperature difference, for example, this may be the vessel 1 may be at a particular temperature and the vessel 2 may be at a particular temperature. So since there is a temperature difference in between the vessel, there is a possibility of flow of the matter, that is the liquid or the component present in the liquid, may move from vessel 1 to 2 or 2 to 1 through this semi-permeable membrane. In actual sense, in a steady state there will be no matter flow between 1 to 2 or 2 to 1. At that condition, the rate of the change in pressure with respect to the change in temperature is known as thermonuclear pressure difference, TPD. So here you can see, if a pressure difference is maintained between 1 and 2, so here now we are maintaining a difference in pressure between the vessel 1 and 2, the temperature will be now constant. So the temperature now it will be remaining constant, but the pressure is maintained. Okay, so now you can see there is a flow of matter from one vessel to another vessel. So now also there will be a flow of matter from vessel 1 to 2 or 2 to 1, but this is purely due to the maintenance of a difference in pressure. So at the same time, when there is a flow of matter, at the same time you can measure how much equivalent amount of energy is also flowing from the vessel 1 to 2 or 2 to 1. So it can be measured by measuring the JTH. So you have to maintain the temperature constant. So for the measuring of flowing of equivalent amount of energy from one vessel to another vessel. And now here you can see, so this this ratio of flow of rate of flow due to difference in temperature and rate of flow of due to matter. So this flow of matter and this difference in temperature, the energy flow is with respect to change in temperature is as zero. This is known as thermomechanical or mechanocalorific effect, the ratio of JTH by JM. So the JTH may be the flow of heat and Jm is the flow of matter, which should be measured in the constant temperature. At constant temperature, this is known as mechanocalorific effect. So the rate of entropy production is given by this formula, which we have already discussed about this entropy production formula. So here you can see, here there will be exchange of energy, exchange of heat, so due to difference in temperature, which is represented here, and here there will be change in number of moles with respect to difference in chemical potential between the vessel 1 and 2. So here it is represented in this way, and already we know the phenomenological equation. So summation of jx is greater than 0. Here there are two, j means the rate, we have to find the rate for two irreversible process. The two irreversible process, one process is the rate of flow of heat, another process is the rate of flow of matter. So for any flux, there should be a force. So the force here for the thermal process, the force is x thermal, and for the flow of matter, we need the force xm. So obviously, so x thermal will be equal to this value 1 by T1 minus T2, and xm will be equal to nu C1 minus nu C2. So here you can see, so here you are now we are equating this equation of x thermal here, and we are getting this value. So T2 minus T1, actually T1 is the higher value. It should, the temperature of vessel 1 will be higher and 2 will be lower. So obviously here the difference in temperature will be carrying a minus charge. So here in denominator we are having T1 into T2. So we can we can assume that T1 is somewhat equivalent to T2. So in common we can take it as T. So T into T, T square. So now we know that the J thermal is d1 pi by dt, and J m will be denc1 by dt. So both are available here. So now we have equated these two equations, and we have obtained this value. So xm, xm is equal to minus, so here you can see it is nu c1 minus nu c2. Here you are having a minus sign also. So nu 1 minus nu 2 is equal to del nu. So del nu is equal to vdp plus sdt. Here we are assuming that temperature will be constant. So obviously vdp will be equal to del nu. So this equation will become 0. So instead of del nu we can substitute the value vdp. So here instead of del nu we can substitute v del p, and here also instead of this 1 by t1 minus 1 minus 1 by t2 you can substitute minus del t by t square. So here we have substituted it and we have got this value. Now J thermal, so here you can see you have to write the cross coefficient also. The heat flow due to change in temperature, heat flow or energy flow. And here you can see there will be a heat flow due to difference in pressure. This is cross coefficient. So we might have done this in the thermoelectricity and also Onsager reciprocal relationship. We have discussed it in detail, so you can refer it. So here Jm is also equal to minus L21 and L22. Actually here there will be flow of matter due to change in pressure. This is flow of flow of energy due to change in temperature. This is the original process. Here these are all cross coefficients, so you can write, and so here you can know how to write the cross coefficient. So L21 is equal to del T by T square. So 21 means there is a flow of matter which is due to change in temperature in between the vessel 1 and 2. So since, yeah, so here based on a reciprocal relationship, the reciprocal coefficients will be equal to each other. So L12 will be equal to L21. So obviously at that juncture, so Jm, when Jm is equal to 0, suppose there is no rate of flow of matter. This is the mechanocalorific effect concept. So when there is no at steady state, there will be no rate and there will be no flow of matter at that juncture. Now you can see when the Jm is equal to 0, obviously L21 will be equal to L12 is equal to L21. So when Jm is equal to 0, so at that juncture now you can see Jm is equal to 0. So here when you bring this value opposite side of the equation, it will become plus. So L21 del T by T square is equal to L22 minus L22 V del P by T. So I will write it in a clear way. So when Jm is equal to 0, obviously if you bring this minus L21 del Tt by T square to opposite side, it will become plus. So Lt1 del T by T square is equal to L22 V del P by T. So we know that the reciprocal relationship will be equal. L12 is equal to L21. So here now you can see from this equation we can find the del P by T, that is equal to minus L21 by 1 by TV. So this will be the resultant equation which we will get. So here you can see, instead of this L21 by L22, you can write it as Q star 21. So in same way, when del T is considered as 0, so when del T is considered as 0, obviously these two equations will become 0. Now when you take the ratio of J thermal by J mechanical, you will get this value L12 by L22. So this can be written as Q star 12. So this Q star 12 represents the heat transfer. So here Q star 12 will be heat transfer from the vessel 1 to 2. So with this this topic is completed. Thank you.